Hi everyone, my name is Li. I'm a PhD student at Duke University. Today, I'm going to present our work, Task-Independent, Privacy-Respecting Data Crowdsourcing Framework for Deep Learning with Anonymized Intermediate Representations. For today's presentation, first, I will briefly introduce the problem we are targeting and the motivation. Then, I will formally define the problem and elaborate the framework design. After that, I will present the evaluation results. Finally, I will conclude our work. Nowadays, deep learning has achieved amazing success in many applications. Such success of deep learning partially benefits from various large-scale datasets, such as ImageNet, Microsoft Cocoa, Celib-A, and so on. These datasets are often crowdsourced from individual users. However, the raw data crowdsourced from individual users often contain different types of private information. For example, given a face image, it's easy to identify the person's gender, age, and other private information, either by humans or by pre-trained deep learning models. Similarly, we can also infer users' private information from other data modalities, such as text data. Some studies have demonstrated that we can infer the demographic information of users from the tweets by leveraging the power of deep learning. The privacy concerns from users on data sharing will hinder the generation or use of crowdsourcing datasets and lead to the hunger of training data for deep learning applications. Therefore, it's critical to design a data crowdsourcing framework to protect the privacy of the shared data while maintaining the utility for training deep learning models. An obvious and widely adopted solution is to apply representation learning, which can transform the raw data into task-oriented features, and the users only upload the extract features to corresponding data collector. Even though transmitting only features are generally more secure than uploading the raw data, recent developments in model inversion attacks have demonstrated that adversaries can exploit the acquired features to reconstruct the raw image, and hence the person on the raw image can be re-identified from the reconstructed image. In addition, the extracted features can also be utilized by an adversary to infer private attributes, such as gender, age, and so on. To step forward, inspired by the GAN, generative adversarial networks, several adversarial learning approaches have been proposed to learn obfuscated features from the raw data. Unfortunately, those solutions are designed for known primary learning tasks, which limits their applicability in the data crowdsourcing, where the primary learning task may be unknown or changed when training a deep learning model. Then, what is an ideal privacy protection framework for data crowdsourcing? The aforementioned privacy and generalization issues motivate us to design a more general and secure solution. Next, I will elaborate the problem formulation and the framework design. In this work, we propose a task-independent privacy-respecting data crowdsourcing framework with an anonymized intermediate representation. The ultimate goal of this framework is to learn a feature extractor that can hide the privacy information from the features, such that attackers cannot infer protected private attributes, even if they obtain the features in some way. At the same time, we enforce the learned feature extractor to maximally retain the original information embedded in the raw data for primary learning tasks. Please note that we do not require any prior knowledge of the primary learning tasks when training the feature extractor. As the figure shows, participants can locally run the feature extractor and submit only those intermediate representations to the data collector, instead of submitting the raw data. The data collector can then train deep learning models using these collected intermediate representations, but both the data collector and the adversary cannot accurately infer any protected private information. The goal of the feature extractor is twofold. The first one is to make sure the extracted features conveys no private attribute. The other one is to retain as much information of the raw data as possible to maintain the utility for primary learning tasks. As the figure shows, we use X to represent the raw data, Z for the extract features, and U as a protected private attribute. Therefore, in terms of goal 1, we expect the intersection between Z and U can be as small as possible. So, we can formulate the goal 1 as minimizing the mutual information between Z and U, and then this optimization problem can be converted to a max-min problem. With regard to the goal 2, we expect the intersection between raw data X and the joint information of Z and U can be as large as possible. As a result, we can formulate the goal 2 as maximizing the mutual information between X and the joint information of Z and U. We would like to refer audience to our paper for more mathematical details. Finally, we can formulate our objective function based on the above two optimization problems. In addition, we also introduce the lambda as a privacy utility budget to balance the trade-off between the utility and the privacy. According to the formulated problem, we design a hybrid learning method to train the feature extractor. As the top figure shows, there are three modules involved in the training process: the feature extractor, the adversary classifier, and the mutual information estimator. In particular, we designed the privacy adversarial training algorithm to achieve goal 1, enabling the feature extractor to hide the private attribute from the extracted features. The path algorithm is designed by simulating the game between an adversary who aims to infer private attributes from the extracted features and a defender who aims to protect user privacy. When we simulate an adversary who tries to enhance the accuracy of the adversary classifier as high as possible, the classifier needs to be optimized by minimizing the corresponding loss function. On the contrary, when defending against the private attribute leakage, we train the feature extractor in path that aims to degrade the performance of the classifier. For goal 2, we propose Maximally algorithm to make the feature extractor retain as much information from the raw data as possible, in order to maintain the high utility of the extract features. Specifically, the Jason-Shannon mutual information estimator is adopted to measure the lower bound of the mutual information. Finally, we can train the feature extractor in an alternative way. In particular, within each training batch, we first perform path algorithm and the Maximally algorithm to update psi and omega, respectively. Then, the feature extractor will be updated according to our defined objective function. Next, I will show you our evaluation result. We implement our framework using PyTorch and perform the training and the testing on our server with 4 powerful NVIDIA GPUs. We adopt 2 image datasets, SaliB and LFW, and 1 text dataset collected from Twitter for training and testing. In addition, we compared our method with 4 privacy-preserving baselines, which have been widely applied in the literature. The noisy method perturbs the raw data by adding Gaussian noise. The DP method means applying the differential privacy, where we inject the Laplacian noise in the raw data. The encoder is a basic DNA-based encoder to learn latent representation, and it holds the same model architecture as the feature extractor in our framework. The hybrid method applies PCA to the extract features from the above encoder, and then add Laplacian noise to those compressed features. First, we evaluate our method on 2 image datasets, SaliB and LFW, and we compare the utility privacy trade-off of our method with 4 baselines. In this experiment, we set young and gender as the private attributes to protect in SaliB, and consider detecting gray hair and smiling as the primary learning tasks to evaluate the utility. With regard to LFW dataset, we set gender and Asian as the private attributes, and choose recognizing black hair and eyeglass as the classification tasks. Here, we evaluate our method with 4 options of lambda, which are 1, 0.9, 0.5, and 0. Ideally, we expect that the accuracy of primary learning tasks can be as high as possible, but can decrease the accuracy of private attributes to a random guessing level. For example, in terms of a binary private attribute, we hope the accuracy of it can be reduced to 50%. As the figure illustrates, although our method cannot always outperform the baselines in both utility and privacy, it still achieves the best utility-privacy trade-off under most experiment settings. For example, as shown in this figure, our method achieves the best trade-off by setting lambda as 0.9. In particular, the classification accuracy of Asian on LFW is about 55%, and the accuracy of eyeglass is 86%. This demonstrates that our method can effectively protect privacy while maintaining the high utility of the extract features. An important step in the hybrid learning method is to determine the utility privacy budget lambda. We also evaluate the utility privacy trade-off by setting different lambda. The top row figures show 3 evaluations on SaliB. You can find that the classification accuracy of primary learning tasks will increase with a smaller lambda, but the privacy protection will be weakened. Such a phenomenon is reasonable, since the smaller lambda means hiding less privacy information in features, but returning more original information from the raw data, according to our defined objective function. we further visualize how different options of lambda influence the utility maintained by the learned feature extractor. This is done by training a decoder with the reversed architecture of the feature extractor. And then the decoder aims to reconstruct the raw image by taking the extracted features as input. Here, we set gender as the protected attribute when training the feature extractor. At the bottom row, the figure shows decreasing lambda allows a more informative image to be reconstructed. This means more information is retained in the extracted features with a smaller lambda, which is consistent with the result shown in top row figures. We also refer the audience to our paper for more detailed experiment result. Since we usually train the feature extractor before collecting the data from users, the transferability of the feature extractor also determines the usability of our method. We evaluate the transferability of our method by performing the cross-dataset evaluations. In particular, we train the feature extractor using either syllable A or LFW, and then test the utility privacy trade-off on the other dataset. As the table shows, the feature extractor that is trained using one dataset can still effectively defend against the private attribute leakage on the other dataset, while maintaining the classification accuracy of the primary learning task. For example, if we train the feature extractor using syllable A and then test it on LFW, the accuracy of gender decreases by 1% compared with directly training the feature extractor using LFW. The accuracy of black hair marginally increases by 1%. The reason is that the syllable A offers a larger number of training data so that the feature extractor can be trained for a better performance. We also evaluate our method on dial, which is a text dataset, consists of tweets. Here, we choose race as a private attribute to be protected, and predicting mentioned as a primary learning task. Similar to the experiment settings in syllable A and LFW, we evaluate the utility privacy trade-off on dial by setting different lambda. As the figure shows, the classification accuracy of the primary learning task will increase with a smaller lambda, but the privacy protection will be weakened, showing the same phenomenon as the evaluations on image datasets. To conclude our work, the feature extractor is learned to hide privacy information in features, and maximally retain original information from the raw data. By applying our method, a user can locally extract features from the raw data using the learn feature extractor, and then transmit the features only. Evaluations demonstrate our method attains a better privacy utility trade-off than existing solutions, and a good transferability across datasets. Thank you for your attention. We refer audience to our paper for more details. Please let us know if you have any question. Thank you.